You need to store a list of items. The obvious answer is an array, and most of the time it's the right one. But there's a classic piece of textbook wisdom that says, if you do lots of insertions, use a linked list instead. That advice sounds airtight, and on real hardware it's often completely wrong. To see why, we need to look at how these two structures actually live in your computer's memory, because the winner isn't decided by the big O on paper. It's decided by something the textbook leaves out. Let's dig in. This is Logic Lab, where computer science becomes something you can see. Today, arrays versus linked lists, and why the obvious choice is so often the wrong one. First, the array. Its defining feature is that all its elements sit side by side in one contiguous block of memory. Because they're evenly spaced, the computer can jump straight to any index with a single multiplication. Element 5 is just the start, plus 5 times the element size. Instant, random access. That's the array's superpower. But that same contiguity is its weakness. To insert a new item in the middle, there's no free space, so every element after it has to shift over by one to make room. Insert near the front of a million-item array, and you're moving nearly a million elements. On paper, that's order and slow. Now the linked list. Here the elements are not side by side. Each one is its own little parcel, scattered anywhere in memory, and every parcel stores the value plus a pointer, the address of the next one. Follow the pointers and you walk the whole chain. This flips the trade-offs. To insert in the middle, you don't shift anything, you just rewire 2 pointers and it's done in constant time. But there's no random access at all. Want the 1000th element? You have to start at the head and follow 1000 pointers, one by one. Finding things is order n. So on paper it looks obvious. Lots of inserts in the middle. Use a linked list, constant time beats order n, but here's the catch the big O hides. That constant time insert assumes you're already standing at the spot. To get there, you still have to walk the list. And walking a linked list is where it falls apart. Here's why. Your CPU doesn't fetch 1 byte at a time, it grabs a whole chunk of nearby memory at once into a fast cache. An array is one contiguous block, so reading it sequentially is a dream. Load a chunk, and the next several elements are already there. The processor flies through it. A linked list is the opposite. Its nodes are scattered all over memory, so every single hop jumps to a random address the cache hasn't loaded, a cache miss, and the CPU stalls, waiting. Even though both are order n on paper, walking an array can be 10 times faster in reality. So the textbook's linked list often loses the very race it was supposed to win. So what should you actually reach for? Almost always a dynamic array, an array that quietly grows itself when it fills up. You get instant indexing, cache-friendly speed, and amortized constant time appends at the end. For the vast majority of code, it's simply the best default. Pick a linked list only for its genuine strengths. When you already hold a node and need to splice it out in true constant time, when you need references that stay valid as the structure changes, or when you're building things like queues and never need random access. Right tool, right job, not just the textbook reflex. This isn't abstract. The default list type in almost every language, Python's list, C++'s vector, Java's array list, is a dynamic array precisely because of cache performance. When you reach for a list without thinking, you're already using the fast one. Linked lists still shine in their niches. An LRU cache pairs one with a hash map to evict the oldest item instantly. Graphs store their edges as linked adjacency lists, and undo histories chain edits together. Know both, but let the hardware, not the textbook, pick your default. Recap: an array is contiguous, instant random access, but inserts shift everything. A linked list is scattered with pointers, constant time splicing, but no random access and brutal cache misses when you walk it. Because real CPUs love contiguous memory, the dynamic array is almost always the right default, the obvious choice, for the non-obvious reason. We've stored lists, sorted them, and searched them. Next, a structure that turns letters into lightning-fast lookups, the secret behind autocomplete on every keyboard you own. How your keyboard predicts words, next on Logic Lab. See you there.